Okay, so thank you very much, Benjamin, Rafael, Rod, and Gemma for such an interesting conversation. Trying to catch up a few minutes. Let's move straight forward into our next next keynote. I would like to invite on stage Marc, Oregon, Chief Technology Officer at Dell Technologies, who is going to talk about building AI context engines on agentic architecture for the AI QC area. So let's hear him talk. Welcome on stage. Let's warm him up with a big of applause, please. Thank you very much. And here you are.
Thank you very much. A great talk by the speakers there on the panel. My name is Marc O'Regan. I'm the Chief Technology Officer for, they're bright. Could we take the lights down slightly, please? For Europe, Middle East, and Africa. And my job is to look at the forward-thinking strategy of the organization to make sure that we don't miss an inflection point in the EMEA region. EMEA being Europe, Middle East, obviously, and Africa. Interesting points being made, some really, really critical points being made by the speakers there. I will do a slight correction on one thing. There is not a moratorium on data center builds in Dublin anymore. It was lifted in 2025. However, there are strict rules around what is required to build new data centers in Dublin, and that involves modern technology, it involves on-grid access, so generators that can actually supply electricity or energy back to the grid in Dublin. The reason that we hit this problem initially, and I know I was part of the engineering build team for the Azure LZ1 in Dublin, and also worked on AWS in 2007-8. The reason we hit this was just so much power was being sucked into those data centers off the grid in Dublin just to facilitate for what we know today as regular workloads for cloud services. Today, those very companies and others are building other types of services and building for other types of services, as are we. They are artificial intelligence related services. So a lot is happening in artificial intelligence today. As I mentioned, my job is in the office of the CTO, where we look, 3 to 5 years into the future and then 5 years beyond. And that's what I'm going to kind of talk about today in terms of what we're seeing in terms of the evolution of compute architecture, the evolution of models, and the evolution of service delivery and where that might and should happen from our perspective and how that relates to energy and energy consumption and energy conservation. So there's a lot of things that we need to be asking ourselves around artificial intelligence. How did we get here? It's nearly 73 years old, would you believe? We all know that, but AI as we know it today really exploded into our worlds on November the 22nd, 2022. And since then, we've had an avalanche of change and an avalanche of opportunities, but also an avalanche of things to consider. Considerations, some of which are being considered very, very carefully, some of which are not and should be. We talked a lot this morning, our speakers talked a lot this morning about what we're doing in terms of building our efforts in Europe, in terms of erecting data centers. We need to be very, very careful about actually where we put these data centers. Any of you who have, for example, been in South Africa, which is part of my domain, in the Africas, will know that without any artificial intelligence being present in the country, there are nightly strikes. If you're in a restaurant eating, that will, the electricity will go down. Quite often, it's happened to me a number of times when we've been there. So what happens when we pull artificial intelligence capabilities into South Africa? That's something that needs to be thought through really, really carefully, and the kind of energy that we build to. Is going to have to be really, really careful as well. There's other things we need to think through. Who owns AI? It's 70 years old. It's being exploded into our ecosystem, 3-4 years ago. Who owns it? Do Microsoft own it? Do OpenAI own it? Do DALL-E own it? Do X own it? Do Dell own it? We don't. I can tell you that. But the real questions in terms of ownership and responsibility has to go right down through the AI stack. That goes from everything, starting with the most important, ethics, bias, responsibility, down into the compute architecture, where that compute architecture is placed, where the data and where the information and where the patterns associated with that information are being exposed, how much energy is being consumed by a data engine, how we can build toward a much more efficient, a much more responsible way of delivering AI into ecosystems. And then understanding whether or not we want to create a relationship with an AI, such as GPT or DALL-E or Mistral or Claude, or whether we want to create our specific relationship with our AI. Now, from a compute perspective, I mentioned that we were involved with building the engines that power Microsoft and power Amazon and others worldwide. We partner very, very closely with other infrastructure providers in this space. NVIDIA are one of our closest partners, as are Microsoft, as I might add, and Intel. But at Dell, we have our own data centers to consider as well. We have 27 data centers of different tierings all across the world. Every one of them are there for our own use, in the sense that they are there to provide services back into Dell and to host Dell.com, which is one of the most widely used websites worldwide. So we know a little bit about putting computers in here, and we know a little bit about how we can actually work with energy over the last 15, 20 years particularly. We know a little bit about why we should, and maybe why we should not, bring water anywhere near a computer. Now, just while I was getting mic'd up a little earlier on, I had a little glass of water before I came on to speak with you folk, and I went to put it down on Adrian, who's our sound man up here, onto his laptop. And he got very, very frightened and took it from me and went, no, Marc, I'll put it over here. That is fear around what might happen if that much of water hits one piece of silicon. Imagine if tons, thousands of tons of water has exposure to hundreds of thousands of pieces of silicon, and what that might do to a data center or to centers of data, which move outside of the data center into the edge. So while water is saving our skin to some degree, and it is, we're interested in all sorts of different, capabilities, liquid cooling, obviously direct-to-chip, as well as other capabilities of handling heat within the data center, so free air, fresh air cooling, things of that nature. Also, the ability to be able to build our compute technologies whereby they can tolerate, not just tolerate, but act optimally, fire optimally at anywhere between 45 and 55 degrees Celsius in the data center. So this is looking at what the compute is doing to its ecosystem as it starts to spin up its cycles and aggressively tear through the data that's being fed to it. These are just computers. These aren't GPUs. These are just computers. And what we've been able to do, and have been able to do for the last 15 years, is get the ambient temperature of the data center up to 45 or 52, 53 degrees ambient temperature, keep it there consistently, and shut the crack systems and the chillers and the things that are consuming massive amounts of energy in the data center right down. So it's an inside-out way of looking at how we actually handle energy from the compute level. We're also involved in these types of projects here. Now, I can give you 10 really good reasons why I think maybe we should consider space-based data centers, and we're very, very involved in a lot of the design phases in and around here from a compute point of view. I can give you 10 or 15 reasons as to why we may not consider space centers. So there's a debate right now, regardless of what you're reading in the papers, there's a debate right now around where we should go with this kind of capability. And they come into everything from locality data, sovereignty, things that we cannot happen on ground, that we cannot govern on ground right now, right through to things that we've never even thought through, like space debris hitting the data center, damaging the data center, and so on and so forth. There's also an energy problem in here, in the sense that the compute architecture cannot leverage off some of the things that we just spoke about, free air, fresh air. So in space, that's very, very contained, and the heat you have is the heat you have to deal with. So there's a number of different things in and around space data centers that we're looking at and working on with our global partners. And so that's an interesting thing to keep an eye on. So a little bit of real insight. I'm not going to spend too much time on this because we have a lot to talk about and very little time to do so. This is a snapshot of really how we see the world today in terms of artificial intelligence. We have artificial intelligent models, large language models. We have small language models, world models, and we have agentic architectures, agents, functions of AI that go and autonomously do things and talk to each other and converse with each other and then make that next step. So they execute against a task and then go beyond that in terms of recommending the next best action, and in some cases even going away and executing against that. Extraordinarily powerful, can take a lot of the thinking tasks, bring it away from the workforce, and then bring the workforce up a level to start thinking about what's better for the organization, even though they have a speciality in a certain domain and so on and so forth. Not getting rid of the workforce as say, but looking at how humans and machines can act together and do so in a lot of cases autonomously. So this has taken us from a place where we used to have a human in the loop to look at what's going on in an ecosystem to having a human on the loop, where the machines are making some of the decisions based on the information and the knowledge that they're gathering. Not just the intelligence, but the knowledge that they're gathering. This is quite a difficult thing to do, and that's what I'm going to take you through in a few moments' time. But we're seeing underwhelming agentic AI systems appear. Why? Because this isn't being thought through. It's not being thought through carefully enough, like many, many things in artificial intelligence. If you let something like this run rip across your ecosystem, you will wind up in massive trouble. These things think for themselves and need a level of control and governance around them in order to make sure that it stays as your AI and doesn't turn into their AI, if that makes sense. So we're seeing that. What we've learned from social media in the past, we're just simply not applying to artificial intelligence, and it's crazy. It's absolutely crazy. As a human race, we've seen polarization, teenage depression, social media algorithms making decisions on what it is that you should consume every day of your life and why. And there is little or no governance over these things. There needs to be. When we go into AI, you can extrapolate that need by about 2,500. We're seeing slowing performance improvements and scaling risk from current foundation models. So large language models are very, very powerful, but they need huge amounts of compute in order to do it. This is frustrating because of the new search engine inadequacies that we see built on old type of designs and technologies. Something new coming in, some of the models that I just spoke about earlier on should fix that. And all of this is leading to what we believe gross misuse of energy. And there is one real fundamental problem with all of this, and that is that AI is limited right now in terms of the AI that you're seeing to language and language models and neural networks that are driving NLPs, which do not have the generalization capacity and the dexterity to exist in a contextual way in our world. Now, there's work being done on that in areas like robotics and so on and so forth, but it's extraordinarily important that we understand that while AI is extraordinarily powerful, and it absolutely is, that there's much more we need to learn about this technology and in terms of what it does for us and the outputs and the experiences and the level of accuracy and context that we're getting from them. And that's something I believe as a technologist really, really needs to happen. They fib, in some cases they tell lies, in some cases they shut down, in some cases they tell you that your cost is this, but your cost is actually that. You can see all the things listed in underneath here. So what's our point of view? If we're saying that, be careful of AI, don't go, and that's not what we're saying. What we're saying is understand what it is that you want to do with AI, make it yours. Look at the foundation models that make sense to you and your organization, pull them underneath your firewall, privatize them, and then pull information that is contextual to you, your organization, and your entire ecosystem into those models. If you do that, literally overnight, you have a much more secure, powerful, sovereign, modern a model than you would have had when this model up here was published. And that's an extraordinarily powerful thing to get into your hands. Next thing you have to start thinking through then is what's happening with these models and what their limitations are. One of the limitations that we've seen in modern artificial intelligence is memory. So if you do create a relationship with an AI, the AI will remember you, and as soon as somebody else comes and creates a relationship with that AI, that conversation is forgotten. So if that's a continual conversation that you're having with the AI, there's a good chance that the conversation you had yesterday will not be remembered today. That's being looked at, so that's the mathematics in behind that. So there's a memory problem. That's being fixed with nested learning. Alphabet are looking at doing this. They will be responsible for the introduction of a paper in 2017. The last iteration of that came out in January, which is looking at this whole idea of nested learning, which looks at continual memory capacity at the compute layer. So if that happens, that improves dramatically. It's a game changer in terms of what AI can do for us. It also dramatically increases the amount of computations that the AI needs to do down at the compute level, which then increases the amount of energy that's provided in order to feed that compute. This morning, I'm just saying this morning because I just read it from a test. There's a test done on our GPUs where we pointed data at our information at the GPU and then just fed it down into the GPU from the compute. As the tests were being done, there was very, very little performance increase until the data was fed into it. Once the data was fed into it and the computations exploded, the performance went up by 2,500%. I think it was 2,340% or something of that nature. I was reading about this only this morning. So we've got to think about the models, we've got to think about the information, we've got to think about the data, and the reason that the performance was so low is because the GPUs were starving for the data. And once you fed the GPUs the data, the performance went up, but the energy went up with it. With the emergence of small language models, a really interesting thing is happening with the likes of Mistral or Gemma. This time last year, there was a test done between Gemma and one of the large language models. So Gemma, just think about this, I think it was 2B2, which is 2 billion parameters, versus trillions of parameters on GPT-5. They outpaced GPT. So small language models are getting smaller, they're getting less energy aggressive, and they're doing just as much with the information on that kind of form factor as well. We're seeing a resurgence of numerical language models, which large language models struggle with. Numerical language models really look at things like not statistical data, but simulation data and so on and so forth. So cellular fluid dynamic code for building simulation engines. And then into this world of what I mentioned earlier on in terms of world foundation models. So these are models that have contextual understanding of the ecosystem that you put them into. And they do that by introducing these agents that I mentioned who go away and understand not just the data that's being fed or information, but the processes and processes that are associated with your specific environment, whether it's a bank, whether it's a healthcare organization, whether it's a manufacturing plant. And they start to converse with each other. These agents start to feed that information, and then they offload this onto a knowledge engine, which feeds back up to the master model. So these are extraordinarily powerful systems that we're heading toward at this point in time. And they kind of look like this. It's a nice slide, but it's horrible to try and get your head around. But this is just a blueprint of an environment where the agents are out doing things in relation to what's happening in the real world, and the context is trapped down in what we call knowledge engines, which invoke on knowledge graphs and so on and so forth. So it goes away and it says, tell me about Marc O'Regan. It goes and it finds Marc O'Regan, then it finds another Marc O'Regan. And then it does a key mapping against those two Marc O'Regans and makes sure that the Marc O'Regan that he presents to you today has no pull-in from a Marc O'Regan over here that might exist somewhere in Ireland also. So it really deals with context, which then hits a lot of different problems that we're seeing around AI in terms of hallucinations and so on and so forth. So this is the way we see the future of computing going. So we would have had semi-adder over here many, many, many years ago, full adder over here in recent and past. So this would be silicon fabrication as we understand it today. And going into the future, this is what we're testing in Dell at the moment. So we're looking at neuromorphic architecture will have a massive impact if it's successful. We've been working with this for many years. It's a completely different way of looking at semiconductors. It's really modeled on how AI engines should be modeled. It's modeled on electrons, which work in our brains, and it takes the compute architecture and the storage subsystem, and it goes like this. So there's no offload that we experience, Van Neumann's architecture and so on and so forth. We get away from that. What does that do to energy? Completely depletes the energy suck that we're actually experiencing today, as does technologies like quantum computing. Down in quantum, we have photonics. So, we have 3D optical computing, where we're using light to transmit the data. So we're using light diffraction to transmit the data instead of electronics. Massive impact on energy conservation. We're also really, really interested in, I mentioned this at the very top of the talk, in battery and modern battery designs and deployments out into data centers around the world. So I'm going to finish on this slide because I know we're out of time, but when we're looking at, just to summarize, when we're looking at artificial intelligence, think where we want that AI to be. Do we want that AI to be outside of your communities and outside of your ecosystem, or do you want to bring the AI into your ecosystem and build for that AI in a way that makes sense to you, your organization, using the compute architecture that you feel is going to be right for you, and understand what it is that you're thinking through when you're thinking through the energy problems that we're coming up today. So sorry to speed up the end there, but I do know that we're out of time, and I'm around for the rest of the day. If anybody has any questions, I'm happy to take them. Thank you.